Well, apologies for the slight delay, but we had a very exciting session this morning. I think this next session will be equally good, doesn't have to be as exciting as that one. Anyway, my name's John Burrows. I'm a Fellow of the Royal Society and a member of the Leopoldina. It was my great pleasure to be invited by Christos Serifos and the Academy here to become a meritorious member of this new Koinon, if I say it correctly. And this is a wonderful new initiative relating our efforts back to those of Plato, his mentor Socrates, and of course his student Aristotle, and the efforts to establish a logical way of thinking. I think bringing in, I'd have to say, what's important to bring in, which is very important to this session, is the use of observations which occurred around 1500 in physics, which really made the jump forward, the use of theory and observations. And that's very important to this session, which is where we're addressing climate change in the Anthropocene and cultural heritage resilience in the Mediterranean. Now, personally, I agree with Drucker, who said, you cannot manage what you do not measure. And so I've been a scientist along with Christos, who I know for a long time now, since he was in Thessaloniki at least, and we've been on the side of observation. So this is part of our efforts here to understand and constrain our theory and essentially global measurements. Climate change goes from the local to the global scale, and we need measurements and theory to address this to enable the projections to be optimal. Now, in this context, we're very lucky to have our four speakers, the first of whom is Petteri Taalas. Petteri Taalas studied at the University of Helsinki. He was also already as a youngster at the Finnish Meteorological Institute and became director there in 2002, and later became, in 2015, Director or Secretary General of the World Meteorological Organization. He's recently returned to be Director of the FMI, and he's going to tell us today about the status of global change and greenhouse gases. I'd just like to remind all speakers that they have about 20 minutes. Thank you very much. I welcome Petteri.
Thank you, John, and thanks especially for Christos for the invitation to come here. It's always a great pleasure to be in Greece, and we have had so good meetings in Greece during the past years. And I used to be part of the ozone community, which where Christos also used to be one of the grandfathers of the work. And John was already telling about my background, so I have been Director General of the Finnish Met Institute and have been also dealing with academic institutions and energy sector as Board of Directors member and so forth. At WMO, we were paying much attention to climate science and communication of climate facts for decision makers, and there we played also a very important role in preparation of the UN COP meetings and also the vicinity of IPCC work. We opened the doors for the hydrological community, and also we engaged the science community more in the work of WMO, and we have the former chief scientist also of WMO with us today. Together with Guterres, we established a program to improve the less developed countries, to improve their early warning services by investing $3.1 billion there. And when it comes to this community, we also established a new program called the Global Greenhouse Gas Watch to better understand the budgets of main greenhouse gases. Now I'm leading the Finnish Met Institute, which is half research institution, half service organization. We have about 400 scientists there, and we have quite extensive climate change program, space program, satellite program, and of course we are providing services in a modern way. And of course, high performance computer resources are important for us, and we are happy to host one of the European high performance computers called Lumi in Finland, and that's what we are using for our modeling work, both climate modeling and numerical prediction modeling. And since I have this kind of physics background, I will show you lots of data, what we have been observing in our climate and also especially in the global climate. So in our case, we are also members of EUMETSAT, which is nowadays very much focusing on greenhouse gas monitoring. We are going to launch this CO2M satellite in a year from now, which is going to be a game changer in monitoring of carbon budgets. And also our ECMWF is nowadays having this Copernicus program where we follow what's happening to climate and factors affecting climate change. And in Finland, I'm also in charge of IPCC, and we have agreed to host a publishing meeting of the first part of Working Group 1 report of IPCC in 2 years from now in Finland. In Europe, we have already joined our forces in monitoring of both atmospheric pollutants, aerosols, and also greenhouse gases. We have a network called ICOS, and we are happy to host both headquarters at FMI. And we have our own measurements in Finland, where we study the budgets of main greenhouse gases in different ecosystems and also different environments. But besides that, we have also measurements going on at Antarctica, in India, China, and we used to have a couple of stations in Russia, but since February 22, they haven't been active. And we can show what has been observed in main greenhouse gases, and you can see that there's been, unfortunately, very steady increase, and of course we are measuring the same concentrations worldwide, but this amplitude annually depends on the site, and we are happy to be in the forested area. And then also the farmlands play a role in this game, and we have monitoring going on at 100 farms, how to bind more carbon to the field, and how to enhance the drought and flooding sustainability of the farmlands. And satellites are becoming more and more important for us, and with satellites we can monitor, of course, air pollutants, but we are more and more monitoring the behavior of greenhouse gases. And EUMETSAT, our meteorological satellite organization, has atmospheric composition related satellite application facility, which we are coordinating, and we are happy to have also Greek partners in this work. And we can, for example, use satellites to monitor where are the hotspots of fossil fuel consumption with these red boxes, and where we have the major emissions coming from biosphere, and you can see these non-renewable rainforests, which are those sources. At WMO, we were concerned that we don't very well understand the role of the land use in the carbon budget, and there's very big uncertainty in this, both in the emissions and sinks of carbon from the soils. And that's why we created a new concept called Global Greenhouse Gas Watch, where we combine accurate ground-based measurements and satellite data to better understand the sources and sinks of carbon dioxide, methane, and nitrous oxide. Now I will show you a set of measurements from our side and also what we have been observing globally. In Finland, we are close to the Arctic, and that's why we have already exceeded 3 degrees warming in our case, and these cold anomalies that we used to have in the past centuries and decades, we haven't observed during recent decades. And by digging old trees from the wetlands and lakes, we can make indirect estimates what has been happening to temperature in northern part of our country, in Lapland, and you can see that the the measured era of the past 150 years, they are showing quite different story from the past. So we have already exceeded this kind of natural variability. And we belong to the area where we have seen an increase of rainfall, especially during the winter half of the year. But let's go to the global observations. In 2024 we broke for the first time this 1.5 degree limit, and the European Copernicus service just published a few weeks ago a report what we have been observing last year, and we didn't exceed 1.5, but the last 3 years as an average we're exceeding 1.5, and we expect that we would exceed that on permanent basis in the next decade. And we have stored more than 90% of the excess heat to ocean, and this has enhanced evaporation from there, and it has also given energy for tropical storms, and there's now about 10% more humidity in the atmosphere, which is enhancing the flooding problems. Sea level rise has doubled during the past 20 years, and there's a growing component coming from the melting of the main glaciers of Greenland and Antarctica, besides the thermal expansion of the seawater. And this glacier melting is contributing more and more to the sea level rise, and this game we have unfortunately lost already. So there's no way to stop melting of glaciers or sea level rise unless we create means to remove lots of carbon dioxide from the atmosphere. And if we go to the Arctic, we have seen a major change in the thickness of ice. We used to have multi-year ice in the past, but recently we have seen mostly one-year-old ice, and last year we broke records again in that sense. And also the extension of the Arctic sea ice, we have seen record low numbers in 2025. And globally, what has been happening to the greenhouse gases, we have seen steady increase in all of those. And in 2024, we saw major emissions coming from the Amazonian area, which was boosted by El Nino, but this is also a demonstration that the Amazonian rainforest area may have become a source of carbon instead of former sink. And globally, we have seen an increase of disasters. Practically the whole world has seen an increase of heat waves. About half the planet has seen increase of flooding cases, and about 1/3 has seen an increase of drought cases. And here in Mediterranean region, we have seen increase of both drought and high temperatures. And the World Economic Forum estimates every year what are the biggest risks for the global economy in 2-year scale and 10-year scale, and in 10-year scale, they estimate that the extreme weather events may be a dominating factor. At the moment, it's number 4, and we have wars and disinformation issues that Jeffrey Sachs talked about. And how is the future? We are heading towards this intermediate direction, 2.5 to 3 degrees at the moment, instead of low, which is 2 degrees, or 1.5, which is this very low. At the same time, we are changing the soil moisture conditions, and some parts of the world are becoming drier, like the Mediterranean region, Southern Africa, both Americas, Eastern Asia, and Oceanian region. And that's having a negative impact on our food security in the future. And if you look at these species here, you can see mostly red and yellow color, which indicates that we are supposed to lose yield of major species. And finally, how the emission situation looks like. China is at the moment responsible for about 30% of the emissions, and European Union about 6% of the emissions. And if the European targets will be reached, we will be in charge of 4% of the emissions. So far, USA has been reducing their emissions, but what's happening now at the government level is a little bit different story, as we just heard. And the emissions in Asian countries are growing. China may have reached their peak already, but India and the rest of Asia is a slight challenge. In Europe, we have been reducing emissions, and the scenario is that they will be reduced further in energy, transport, housing and agriculture sector, and we will compensate part of that by taking care of the land use. And finally, how the mitigation perspective looks like. We have been reducing the prices of climate-friendly energy solutions. Wind and solar energy are more profitable than classical fossil energy, and also the prices of batteries and electric vehicles have been dropping. And the sales of electric vehicles has been increasing, especially in China, where it's cheaper to buy nowadays electric vehicle than classical fossil fuel-based vehicle, and they are at the same time solving their air quality challenges in big cities like Shanghai and Beijing. And also here in Europe, we have been seeing a growth in the sales of electric vehicles. In USA, less than the global average. And finally, how to solve this problem? We have to stop using fossil fuels, as everybody knows. That's 2/3 of our problem. Then this methane is responsible for 20% of our problem, and deforestation of the non-renewable rainforest is about 10% of our problem. And if you look at country groupings, G20 countries are responsible for 80% of the emissions, and the richest countries, G7 and European Union, they are responsible for 30% of the emissions. So whether we will reach the Paris numbers is very much in the hands of these BRICS countries and countries like Saudi Arabia, South Africa, and in Indonesia. So if they are able to enhance their mitigation efforts, we could see an improvement. And there's a debate going on whether we should, as consumers, play a role there. My own thinking is that the frames have to be set by governments and players like European Union, but of course we can play a role by touching our means of transportation, our diet, and in our latitudes in northern latitudes, how we, for example, heat our premises, and how much we buy goods which are produced by using fossil energy, and that's not good news for the Chinese production so far. And finally, what are the wider security implications of climate change? My main concern personally is how to feed the growing population of the planet, and what kind of refugee challenges we will see, for example, in Europe, which are clearly having political implications as well, as we saw in 2050. And if we are going to be successful in climate mitigation, then countries like Russia or the Arabic countries or even rich country Norway may suffer, and which may have political consequences. And we have seen the interest towards Greenland by Trump, which is of course related to natural resources, not so much to defense, but there are also other players on board. And I already showed this global economy issue, and in Europe, Mediterranean region is going to be a challenging region because of higher temperatures and drought, which is having negative impacts on tourism and agriculture here. And this is my last slide. Actually, Jeffrey Sachs was already mentioning this, and I disagree with him when it comes to the rational action of Russia, but at the moment European Union and China are the rational players in the world, and also in climate policies unified forces would really make sense. In case of USA, we are a little bit hopeless, despite the states have independence here, but China and USA China and European Union could clearly find a common tone here. That's all from my side, and I think that I was almost able to keep my time. Thank you.
So thank you very much, Petteri, and he made an important point about the Mediterranean region being also on the edge. Now, our next speaker is Guy Brasseur, and it's my pleasure to introduce Guy. He studied in the Free University of Brussels. He worked at the Belgium Institute of Aeronomy prior to a short stay at the Max Planck Institute, where we overlapped, and then became director of NCAR's Chemical Sciences Division, later head of the Center for Earth and Sun Systems. Over here, he became Max Planck Director of Meteorology, and also set up the Center for Climate Services, which is now an HGF Helmut-Gesellschaft. So a remarkable scientific and science management career. It's a great pleasure. I'm not going to list his many awards. He's also a member of several academies. It's my pleasure now to introduce him as a scientific speaker today. So, Guy.
Good morning to all of you, and thank you very much, Christos, for inviting me. I will talk a little bit today on something that's a bit of a new topic for me. I call it Sky Architects, Promises and Peril of Climate Manipulations. So, if we go back to the beginning of the 20th century, just in the wake of economic development, industrial development, belief in technology, some people were advertising not only the possibility of predicting the weather, but in reality to change the weather. And there was an offer made in the US that said, think about it, rain when you want, sunshine when you want it. And so already in the 19th century, the idea of inducing rain and fascinated people really, and some people were worried about another aspect, which was the damage from hailstorm, in particular wine grower in France. So the only way that was available at that time to deal with that was for priests to ring the bells in the churches, for citizens to deploy cannon, anti-hail. Unfortunately, it didn't work very well. Well, around 1946, after World War II, some companies like General Electric said that they could develop techniques to produce artificial rain and basically seeding silver iodine in crystal in the atmosphere from airplane, and that would create rain where we need it. And today this is still done by a number of countries. China has 37,000 people work on artificial rain. But of course it was also appealing to military people who believed that they could disturb the environment by creating artificial rain. And so it was used, for example, by the American military in Vietnam to try to break the Ho Chi Minh Trail and avoid the North to bring weapons to the South. So all that happens, all that was to a certain extent controversial, but it gave the idea that maybe we could do bigger, go beyond regional or local weather and transform the weather, the climate of the planet. So with climate change on the horizon, manipulating climate might be a way that technology could bring to in reality to solve the problem that we are facing. So it would require, of course, to modify large energy flow in the Earth system and to look at the problem as a whole for the planet. And of course, such manipulation raised not only scientific question. The science might be there soon, but there are other aspects. There are philosophical aspects. There are moral aspects. There are ethical aspects that exist around modifying deliberately the situation that nature is controlling. And so I'd like to bring up some of the views that are coming from what I call the architect or the engineer of the skies or the heavens, versus a number of people who ask for more care, more thought about it before we jump into something that might appear to be appealing. So what is the rationale for modifying climate? Let's look at the evolution of temperature that the paleoclimatologists are providing over the last 3 million years, which is here on the graph. Temperature has been, of course, fluctuating somehow, but it hasn't been changing that much, in particular in the last Holocene optimum. If we look at the prediction of the models or the projection of the model for the situation in 2050 or 2100, the mean temperature of the planet, the average temperature of the planet, will be outside the bound that you see here, higher than ever in the last 3 million years. So we're entering in an unknown future, in an unknown environment for the planet. And of course, we know what happens in the last century, in the last decade, where CO2 concentration has been increasing as a result of human activity, and in parallel, the temperature has been increasing. You heard that. And if we take again the models that provide some guidance in our thinking and try to look what would happen under different possible increase in CO2 in the future, different scenario, we can see that the business of usual, which is probably the largest warming that we see here, leads to changes in temperature of a few degrees globally. But if we look at the Arctic, we're talking about more than 10 degrees changes, and clearly we are in an unknown environment, but the models show that this unknown environment might not be very satisfactory for society. So we have climate change, and we heard about what we already observed. We just heard the previous talk, and we also heard about the solutions. And basically, we have 3 solutions that we can discuss. First of all is climate mitigation, in other words, to reduce the emissions, to limit the severity of global warming. This is probably, by the way, the best solution and maybe the only solution. If we don't do that, we might have to adapt to climate change. We might have to adjust to ecological, social, and economic disturbances in the system to better cope with the impacts that will result from climate change. But then we have also the possibility of climate manipulation, or what we call geoengineering, where deliberately we interfere with the climate system. And I'm bringing up a graph that is very similar to what John Schellhuber showed yesterday. The curve in green would be what we call business as usual. If you do nothing, that's what's going to happen. We're going to have a huge warming. If we do mitigation, we'll go down a little bit and we might follow a curve like the yellow curve, where we might go over the target that's shown here in red with a certain overshoot for a number of years, perhaps number of decades. And this is the one that the people providing or suggesting geoengineering say, well, we should get rid of this overshoot by doing something. And so what can we do? Well, to answer that, we have to look at the energy balance associated with radiative transfer in the atmosphere. We have 2 kinds of radiation. We have the solar radiation on the left that shows that part of the light that is incoming is reflected to space, and we could change the level by which it is reflected. That would be one way to infer on the system. On the other hand, we have the thermal outgoing radiation emitted by the surface of the Earth and the atmosphere, which is partly blocked by the presence of greenhouse gases. And so we could reduce the level of greenhouse gases to let more radiation go back or go to space ongoing from the Earth. So we have two ways. Either we remove CO2, carbon, as much as we can, or we create reflection of the sunlight, and so we have either what we call carbon dioxide removal or negative emissions, or we have the possibility of solar radiation management. Let's go quickly on two of them. The first one, negative emission removal of CO2 from the atmosphere, is not something that raises a big philosophical issue, but you have different ways you can do it. I listed some of them. I don't want to go in much detail. You can plant million or billion of trees. You can seed the ocean with alkaline substance. You can fertilize the ocean to reinforce the biological pump. You can pump up deep water from the deep ocean so that you have more capability of absorbing CO2 from the atmosphere. We can accelerate CO2 capturing through rock weathering by, in fact, putting on the ground on agriculture land, for example, some material that would produce what rock weathering is doing. You could also capture CO2 directly from the air, and those are shown here, and they have been proposed, and of course they are still to a large extent under discussion. The other option is to manage solar radiation and increase the reflection of the solar energy back to space. Now, already in 1955, the brilliant mathematician of John Neumann, you know him, some people call him a man coming from the future. He wrote a paper saying, can we survive technology? And he said, had the dust of the eruption from Krakatoa in 1883 stayed in the atmosphere for 15 years, reflecting sunlight from the Earth, it might have been sufficient to lower the world temperature by 6 degrees Fahrenheit. So this idea was taken over by a number of scientists later on. First, in the Soviet Union, Mikhail Budiko proposed to inject small sulfur particles, just like the volcanoes in the stratosphere. And Paul Crutzen made a number of calculations. He promoted this idea, and he said if we inject every year 1 to 2 teragram of sulfur in the stratosphere, it will reduce the forcing by about, let's say, 1 watt per square meter. Remember that if you double CO2 in the atmosphere, you generate a forcing of 3.7 watt per square meter. So it would do something. And what about the cost? And you would say, well, the total cost would be between $25 to $50 per capita in economically advanced country. And so you should compare that with the cost, the benefits that for society, the cost for society of not doing it, and also if you compare it with military expenditure, it's more. So modelers have been looking at that in more detail, and I'm going to show you here one example. You saw on the bottom, this in black, the CO2 emissions, assuming that mitigation is taking place so that you go around 2040 to a maximum and then it decreases slowly. And then, of course, if you take this scenario, you get the temperature on the upper part of the graph with an overshoot of about 3 degrees. And John Schenhuber showed you what it means, 3 degrees. It's very high. So if we inject now SO2 as in the lower panel, we may be able to limit the temperature globally to about 2 degrees Celsius. And so geoengineering in this case apparently would be of great importance. However, if we look point by point in the planet and see how, for example, the warming on the left, business as usual, would be compensated by injecting sufficiently sulfur in the stratosphere, we would have a delta T, a change in temperature as shown on the right panel, showing you that even though we compensate a lot of the CO2, we do not do uniformly. There might be regions where we have losers and regions where we have winners. And so there is, of course, a problem of how the Earth would respond to some proposition like this, in particular, how the precipitation system would respond in certain regions of the world. Now, there are other ways than injecting sulfur particle in the stratosphere. You could make a cloud brighter, you could make the Earth's surface brighter by some ways, you could make the ice that's not completely white brighter, or you could display a big parasol in space that would be positioned at the Lagrangian point L1 and would reflect part of the radiation before it comes close to Earth. And you see here a number of initiatives that have been proposed to brighten the surface of the Earth and reflect some of the light, including the injection of stratospheric aerosol that Paul Crutzen and others had proposed. So let's see, and let's try to answer a question. The science seems to be interesting, but can we really save the climate with technology? Well, people have been looking at those different methods, looking at the effectiveness and the affordability, and you see that basically you have methods that are effective and affordable. You have other methods that are less effective and also less affordable. And so economists that are interested in geoengineering have been discussing in detail. So let's finish by thinking a little bit about the pros and the cons of doing this. As I said, even if the science is convincing, we should go beyond that. Of course, the people who defend geoengineering have a number of arguments. They just say, well, it reproduces essentially, if we inject in particular a sulfur particle, it reproduces volcanic eruption, and we know from the past, from experience, what a volcanic eruption is doing. They also say that it's relatively inexpensive compared to the cost of global warming, and even it's cheaper probably than mitigation policies. And I think this is a very dangerous argument, but it would not disturb very much our lifestyle, and probably much less than mitigation, which would require effort by everybody. And I say this is a dangerous argument because a number of people might say, well, let's do geoengineering. It's much easier, and we don't have to mitigate. So problem is solved. However, there are issues, and we have to raise them very strongly. Operation will probably benefit some area of the Earth, so some population, and disadvantage others. Some models show, for example, that the monsoon could be displaced, and that could be dramatic for India. There will be side effects, as I mentioned, the precipitation, the monsoon, maybe the ozone layer could be affected by the presence of sulfate in the atmosphere, and those effects are still poorly understood. The governance is a major issue. The governance of operation of trying to do geoengineering would or could ignore the principle on environmental justice. It could generate tension. Some people could do it for their part of the land against others, would generate probably tension between nations, and could lead to a logic of militarization. So there are issues, and that require certainly that the population take attention to that. I think the way forward is the following today. Absolute priority must be mitigation, reducing greenhouse gas emission. Don't get entrained by those people who say, just go on, pollute. We'll find a way technically to solve it. This is very dangerous. Global governance, major issue, should be under the control of a large number of organizations. Governance should control the use of geoengineering technology, should make it consistent with fundamental rights and inclusion of a lot of partners and countries in the world who would be affected. In the meantime, and before all that is established, I think we need a moratorium on, in particular, the deployment of the technology that would modify solar radiation by injecting sulfate particle in the atmosphere. Now, in spite of that, in spite of the fact that we shouldn't go ahead, we should probably continue research on those topics. But the research should be rigorous, ethical, transparent, with a critical reflection on possible impacts and a full information of the citizen of the planet. And I'm going to close by citing one of my former friends, Ralph Cicerone, who was the president of the US Academy of Science. And he said, we need to distinguish between really research and actual intervention. Research is necessary to reduce ignorance. The freedom of research has a moral value in itself. But there is a step between the research and the implementation, because human aspects, societal responses are crucial in an operation, an implementation that would affect the single planet that we have at our disposal. Thank you.
Excellent, Guy, and thank you very much. I think you've raised an important topic there, which is a number of important topics, but one particular I just think is a good link to our next speaker, which is actually, we've been doing geoengineering on the Earth since effectively the Neolithic revolution without thinking about it. We've been changing the Earth's surface in a great way. Now, our next speaker in this area is Andreas Karamanos, if I say it correctly. He's a man of Athens, but also a man of the world, because he's studied at the Agricultural University of Athens. He became later on a professor, I think vice rector and rector, if I'm correct, and is also, of course, a member of the Academy here. But he's also been a man of the world because he's been working both for the government, for UNESCO, and for the EU. So he's an expert in surface, and we welcome him to this very important meeting, and thank you very much for coming. And please stay on time.
Thank you for your kind words. Thank you, Chairman. Dear guests, ladies and gentlemen, my presentation is lying on two keywords of the session: the cultural heritage and the changing climate as well. I'm going to speak about the natural vegetation, which is important component of the cultural heritage. We know that cultural heritage is divided in so-called tangible and intangible culture. Part of the tangible culture is the natural heritage, which includes naturally significant landscapes, but also biodiversity. In 1972, the UNESCO World Heritage Convention established that biological resources, including plants, are the common heritage of the mankind. Or, as was expressed in the declaration, plants need to be preserved as part of the world heritage of mankind as a whole. We all know that cultural development is closely linked with agriculture through the domestication of wild plants and their cultivation. We also know that plant products are utilized for several purposes: food, fiber, sheltering, and so on. But we also have in mind that plants have been embedded in people's cultural traditions and narratives, their religious beliefs, and others. I'm going to give some examples of the close links between cultivation and civilization in different areas of the world. You might well know that. But we know that the cultivation of cereals and legumes in the Near East is the cornerstone of the civilizations in Mesopotamia, Egypt, Palestine, Greece, and Rome. If we go to another continent, we find that maize is the cornerstone of the civilizations in Central and South America. And we go to the Far East, we know that the cultivation of rice is the cornerstone of civilization there. I'm going to give you some examples of the depiction of crops and natural vegetation in pieces of art and everyday life. Going back to 15th or 14th century BC, in which we have some frescoes from Santorini, is the Cycladic civilization, in which some persons are working with plants around them. What are these plants? They might be lilies, they might be crocus plants. Anyway, we have to bring in mind this famous fresco from the Knossos, the prince with the lilies, just to enforce this view. Several centuries later, we find in a coin from the Metapondion was a Greek colony in southern Italy, the depiction of the inflorescence of a barley plant, the inflorescence and the final leaf. So this goes back to 320 to 290 BC. The next example is, comes from a vase of the 5th century BC, located at the British Museum, in which a young man sitting in a chariot is the king of Eleusis, Triptolemus, who grasped with his left hand a bunch of wheat plants. And on the right-hand side, the figure is the goddess of agriculture, Demeter, who is blessing the young man. And we finish with another thing, rather different. There is a plant called Acantha, Acanthus mollis, which has some very nice leaves and, of course, inflorescences. But the leaves of this plant have been used as a model for the Corinthian-style decoration pillars. You see the resemblances from left-hand side and right-hand side. Now, moving away from these examples, we go to a term which might be very familiar to most of you, the biodiversity, which is the variability among living organisms that derives from different ecosystems, including terrestrial, marine, and aquatic ecosystems. The biodiversity includes diversity between species and within species at a genetic level and of ecosystems. So natural vegetation is a part of world's biodiversity. And in this context, plant genetic resources, to which we come later because they are interesting to us, are also part of plant biodiversity. In Greece, we have very rich biodiversity, which is one of the richest in Europe and in the Mediterranean. It entails more than 7,000 terrestrial taxa. Taxa is a botanic term originating from the Latin taxon, which means the plant species and their subspecies. So it's very rich biodiversity. Yet, part of this biodiversity is at risk. They are species considered as vulnerable or threatened. And all these species are included in a book called the Red List of Threatened Species. Why all these species are threatened? For several reasons. First of all, the change in land use we're experiencing in the last years. Just bring in mind what is happening in the Amazonian basin where all the forests have been destroyed, and of course, a lot of species within these forests have been brought to extinction. The loss of habitats. When say habitat, we mean the areas and environments where these different species thrive. So lots of habitats have the same negative effect on biodiversity as the change in land use. Of course, the overuse of natural resources, pollution, and finally, invading species from other areas which compete with the local vegetation. On top of that, of all these factors, now has come the changing climate, which also affects adversely the local flora. By what means? First of all, by direct impacts on plants. For example, the effects of temperature. The effects of temperature affect the survival and the development, the reproduction, the distribution, and the behavioral patterns of local flora. The impacts through biotic interactions between taxa. This is the so-called the change in competition patterns, which is brought about by the changing climate. And of course, the impacts through the changes in abiotic factors, such as droughts, floods, thermal incidents, forest fires, etc. All these factors, as we said, are a potential danger to biodiversity. How plant species can respond in a changing climate? First of all, by adapting to the new conditions, by developing changes in their morphology, anatomy, or physiological mechanisms, by migrating, when possible, to habitats similar to the original ones, through, for example, through the dispersion of their seeds or their propagating material by rain or air in distant areas. And the most undesirable effect is to be forced to extinction for species which are close to the margins of their colonization or with small populations. We now come to the interesting part of this presentation, the plant genetic resources for food and agriculture. They include, apart from the crops and their varieties, the crop wild relatives and the local varieties or land races. Of course, all of them are part of the world's biodiversity and of course are on the same risk as the other flora. I have here to say that the progress in agricultural production for the first 100 or more years has been achieved mainly by introducing increasingly productive and cultivation which are adapted for specific environments. This extensive use of these productive cultures has restricted the pool of the available genetic resources and led to a phenomenon called genetic erosion. This means the loss of individual genes or gene complexes. So, the genetic erosion constitutes a major threat for crop wild relatives as well as for underused local varieties and land races. We have thought about crop wild relatives. As the term indicates, these are wild plant species that are more or less relevant to, genetically relevant to the crops, and some of them may also are crop ancestors, which, this is the important thing, were not domesticated. As regards the local varieties and land races, they are plant populations which are genetically non-uniform that have evolved over generations through farmer selection and adaptation for specific environments. What are the major properties and the important properties of these two groups? First of all, they are well adapted to marginal environments. Secondly, most important, they are endowed with a rich reservoir of genes for resilience against both biotic and abiotic stresses, which are, of course, very closely related to the situation we find through climate change. Some of them, they have also nutritional and flavor characteristics. Just an indication of the abundance of crop wild relatives for major crops in the Mediterranean. We can see on the right column that there are quite a lot of taxa, very close, the relatives to the cultivated crops we found in our region. If we now go to the land races and local varieties, I have only to refer for the Greek situation that the national list of local varieties of field, vegetable, and tree crops in Greece contains more than 1,500 identified registrations spread over the mainland Greece and the islands, and this data referred back to 2022. The number will be even larger 4 years later. What are the important characteristics of crop wild relatives and land races which are useful for inducing crop resilience under climate change? I'm just quoting the resistance to drought, the resistance to salt, the resistance to high and low temperatures, the resistance to pests and diseases, the ability to compete against weeds, and of course the lodging resistance, which is the fall from the vertical position of the cultivating crops. Just some examples of utilization of crop wild relatives for crop improvement. If we wish to induce cold resistance in wheat, we use a wheat ancestor, which is called Triticum monococcum. The photograph shows the ears of this plant. If we wish to induce salt tolerance for beets, either red beets or sugar beets, we can use the ancestor, which is Beta maritima, a halophyte, which means a crop which is adapted to use close to the sea. We now come to a very important characteristic, which is drought resistance, and now I'm referring to a monograph which was published from a research of the Agricultural University of Athens, and it was awarded by the Academy of Athens, in which we found that there were detected quite a lot of differences between land races, between populations of wheat and durum wheat in Greece. This concerned both their responsiveness to drought as well as the drought resistance mechanisms themselves. And there are many other paradigms on that subject. For several crops in which drought resistance was induced by using crop wild relatives for chickpea, barley, rice, tomato, etc. For inducing resistance to pests, fungal diseases, etc. We have successfully utilized crop wild relatives for a number of species, which you see in this slide: barley, wheat, tomato, potato, and so on. So it follows that crop wild relatives, land races, and local varieties must be considered as invaluable resource in breeding for adaptation to climate change. How we can do that in practice? We have two stages to do that. The first stage is first to collect and effectively maintain and conserve the local material. This is important because quite a lot of material suffers a continuing loss of diversity and the erosion of genetic variation, as we have already said. On top of that, a lot of this material is also very susceptible to climate change and, of course, to soil desertification. In order to be effective on that, to safeguard all this material, considerable measures have been taken, both in Europe and worldwide, to save this material in institutions called gene banks. We save the propagating material in gene banks. We have one in Greece, but there are many all over the world. Or we can safeguard and we can conserve that in situ, in their place in the local environments. There are many conventions active in this respect. This is not a simple thing to conserve this material. It requires special research on several issues. First, the optimum population of the material, of the samples. Then about the decay of the diversity in collections. The effects of different regeneration practices were followed. And finally, it is important to use molecular methods in genotyping these entire collections, just to know what they can offer. The last stage is the incorporation of the desired genes from the wild relatives to the crops. This, of course, presupposes that we know very well the chromosomal location for the important characteristics. And of course, a very useful tool is the plant genome sequencing, which is extensively used in the last years. Once we have done that, the second stage, the most important part, is to incorporate the useful genetic material from the wild negatives to crop genotypes, using either conventional plant breeding techniques, crossings, back crossings, etc., but also the new tools we have in our disposal, which are the genetical engineering and others. And with all of that, I am coming to the end, and I thank you very much for your attention.
So thank you very much for that very nice overview, and it's very stimulating. We now come to the last speaker of our session. He may not be well known to you. He's, of course, our organizer and I'm glad to say my friend. So Christos, are you going to play for us? That would be afterwards. That would be very nice. That would be very nice. We've been recommending it. Now, just to give you your proper introduction, actually, Christos and I were both born under the British Empire. And in fact, my uncle was in Alexandria at around that time, but I don't think we're relatives with the 8th Army. You've had a wonderful scientific career all over the world, but particularly I'd like to point out your contributions to ozone research in Europe, but also the world. So you played a great role in both the stratospheric and tropospheric ozone research of the EU, being a very important advisor, but also leading the International Ozone Commission. You've been president in 2 universities in Greece at least. You're also a leading member of the Academy in Athens and head of the atmospheric physics department. You're also the leader, together with your colleagues, or you've been leading your colleagues in creating this wonderful new initiative to try and bring the world together on climate science, among other things. Thank you very much. Welcome to Christos.
Thank you, dear Chair, dear colleagues, ladies and gents. There is no gene to the monuments. We cannot modify their essence. They are built, and the climate crisis is there. They stay still, suffering without talking, without reacting, only they can deteriorate, nothing more. The Mediterranean, where I will focus the effects of climate crisis to historic monuments, UNESCO actually, is one of the hot spots, and according to the latest all IPCC reports. I'll show you some examples of destructions that have affected the Olympic Zeus temple. There was a parallel session by Professor Manolis Kores on the structure and the deterioration of that monument in the next hall. And you can see that during a terrible storm, one of the 13 standing columns has fallen. The place where the Olympic Games used to operate in ancient Olympia was threatened by forest fire. Floods are always threatening San Marcos Square. And we thought that it's time that we create an index to monitor the rate of deterioration of a monument and to try to apply this index by using an ensemble of 21 climate models with my colleagues John Kapsomenakis, Kostas Dubis, and others. The importance of the factors affecting, you can see them numbered. Actually, the hot days, the number of hot days is a sign and an index for extreme heat. The number of days with fire weather conditions, another, if the monument is nearby a forest like in ancient Olympia. The number of days per year exceeding the 99% percentile in precipitation is proportional to extreme rainfall. The number of frost nights, the mean sea level rise for monuments that are near the sea, the aridity index, about 1/3 of the Greek land, of about 1/4 of the Italian land and Spaniard and Spain are threatened by aridity. And of course, in the Mediterranean, we have the famous confrontation of Africa with Europe. And we have seismic activity that is also measured, can be measured by the acceleration of the movement of the Earth. So looking with these 21 models, how they evolve under two climate scenarios, IPCC scenarios, one can see that all are worsening the story, particularly after 2050. In fact, as our dear modelers know here, most of the models, they don't converge to easier decisions and for easier solutions after the year 2050. One can see that extreme fire, weather fire, extreme precipitation goes up. Of course, in the worst case scenario, the doing nothing, actually, it's the curve that goes faster. Here are the frost nights that they are the only index that is being reduced with time. and the sea level rise is obvious. Both speakers, Petteri, Taalas, and Brasseur, have shown that the sea level is being doubled now in rate of increase. The places where seismic index is threatening the monuments, here you can see the areas where the UNESCO monuments are. There are 240 monuments, historic monuments under watch and possible threatening. The index we have somehow created is an index based on the variables that I have shown before, and we gave it a name, Heritage Hazard Index, which has a range of values according to the statistics that we have done, between 0 and 12 as absolute numbers in that scale. 12 is the worst case, and from 0 to 4 when we include the seismic factor. Here one can see in the upper two slides the moderate application of the Paris Agreement, and one can see the numbers of the number that the indices take, and below is the doing nothing scenario for all 240 monuments. The number of the most threatened monuments per hazard can be shown, is shown here. And in fact, there's no time, but the number of monuments grouped in 4 categories show that there are 12 or 16 monuments selected that are threatened most according to that study. These 12 monuments, half of them are in Greece, unfortunately, and the reason that makes worse the case for Greece is the increased danger of seismic activity. And they include also monuments in Croatia, in Albania, in Turkey, in Spain, and Italy, of course. So you can see these monuments listed here. We have written a recommendation to His Excellency Secretary General Gutierrez, and he adopted that threat to be included in his urgent decisions to be taken. Exactly 1 o'clock. Thank you so much.
Well, I think we have to thank our speaker for a number of things, but also for helping us to get towards lunch. But first of all, I'd like to thank all of the speakers again. Everybody, we give them a round of applause. And sessions begin again at 14:30. And of course, great thanks to Christos.
Yes, thank you so much. Thank you.